Welcome to Equinox, where Rob and I are striking the balance between the light and the dark. This is episode 36. My name is Joseph Darnell, and I'm joined by the one doctor on the show, Robert Carter. Hey, Rob, how you doing?
Hey, Joe, I'm doing fantastic. Hope everyone in the audience is feeling that way too. If not, maybe we can just encourage them because life is so cool and there's so many amazing things to figure out.
Yes, life has been so cool for the past week. We actually needed to take a week off. We were trying to schedule it around the weekend, but then I was having very bad internet reception, so we had to postpone. Sorry, everybody who missed that episode. We'll make up for it with this one. This one's going to be good.
I think
Feel
so.
good about it.
As soon as we picked this topic, I was like, oh, this is so cool, so fascinating. Oh, man, I can't dig. So we have a lot of cool things to share with people.
Yeah. But you just had a birthday. Happy birthday, Rob.
Well, thanks, man. Appreciate that. And thank you for the birthday party.
Oh, you're welcome. I almost forgot about that. But it was a good time.
It was a
And
good time.
it was great to see all of you. Are you feeling good about this new year? You're happy with your last, was it revolution around the sun? Happy to have that one down and ready to start a new one?
Yeah, I'm looking forward to 2021. There's a lot of new things on the horizon. Therefore, everyone's life in general is probably going to be better next year than last year.
Mm-hmm.
Speaking of days, we just had a Friday the 13th.
Yes.
And I got to thinking about days and why we pay attention to some days and not others. So I started looking at why is Friday the 13th so special? And you know what I learned?
What is that?
Nobody knows.
Really?
Yeah,
There's
it's a
not-
total enigma why a Friday on the 13th is such a big deal.
It wouldn't like coincide with another horrific world event that happened on the 13th on a Friday, or somebody's death, or maybe a curse.
Well, some people are saying because there was 12 apostles plus Jesus makes 13, and Good Friday, therefore 13 and Friday together, or who knows? Nobody knows. All speculation.
That does sound like a good possibility.
Maybe it's kind of speculating, it's stretching it, I think.
Yeah, all of it's speculative, though.
Yeah.
Nobody likes the 13th. It's a bad number, bad luck. But we don't believe in bad luck on a equinox, right? This is a science podcast.
No, of course not. But then I was like, all right, what other special days are they in the year? I said, oh, April Fools. What's the background behind April Fools? And you know what?
Yeah.
Nobody knows.
Really?
Yep.
Well, okay, if you don't know the background, then how far back do you even know about the holiday?
We're not
surely
sure.
they know where it originated in the... Really? So it kind of like predates what we recognized?
Well, some speculate it goes back to when we flipped over to the new calendar system, and some people didn't realize.
The Gregorian.
Yeah, some people didn't realize that the new calendar, and they also moved the year. So the new year used to be for most places at the vernal equinox, but then they bumped it to the beginning of January. Well, the Romans did that, et cetera, et cetera. There's all these confusions, and no one really knows.
Huh.
So it's like, okay, what's
April
another
Fool's Day.
famous day? Oh, that would be the Ides of March, right? From the Julius Caesar in the Shakespeare play Julius Caesar. Beware the Ides of March. I was like, oh man, what's an Ides? And so I had to look it up. It means the middle of the month.
Beware the middle of the month.
There's nothing special at all. It's just the midpoint of the month. It's called the Ides of March. I was like, oh, come on.
Really?
So all my special days that I was looking up, honestly, they were a big poof. There was nothing to them. People are weird, man. We pay attention to things that mean nothing.
We just had a Friday the 13th. Yeah. That is so weird. So there's typically 2-3 Friday the 13th in a year, maybe even less.
Yeah, it depends. Yeah, it's pretty random. One of my friends on Facebook, strangely, I didn't know he was paying attention to Friday the 13th, but he's posted that it was like, X number of hundreds of days since the last Friday the 13th.
Oh.
It might have been 400 days or something like that. It's been a long time.
Neat.
Strange. It's a fun day anyway.
Interesting.
I like celebrating Friday the 13th just because everyone else is like afraid of it. So
I
say you're crazy. This is gonna be a good day for me.
Very nice. Very nice. You actually brought up that there was something else that was peculiar that is a developing discovery, or maybe just a new piece of research concerning the longevity of escape velocity.
Yeah, what a
but
weird
for
thing.
lifespans, not for... When you brought this up, I thought you're talking about longevity of escape velocity.
Space. How long escape velocity lasts when you're flying through space?
Yeah, what's the speed that a shuttle needs to take to get out of the atmosphere? But this is not what they're talking about.
No.
This is intriguing new development.
Yeah, it's talking about human lifespans. And can we get to a point where mathematically or actuarially we can theoretically have an infinite lifespan? So imagine that over the course of a 5-year period, that human lifespan on average increases more than 5 years.
Yeah, so when I was maybe a 15-year-old, I remember people saying that the average person lives to be maybe 70, 75.
Yeah. Well, that keeps on going up. But if it goes up at a rate faster
Mm-hmm.
than the time span between the two measurements, we're actually on a hyperbolically increasing curve, or at least a parabolically increasing curve. And if we're going up that fast, we're extending our lifespans faster and faster, and we're close.
That is really wild.
Yeah,
Wow.
we are close because I mean, literally, we can almost got to the point where they can grow you a new liver, a new kidney, a new heart.
Yeah, like you were saying, there's somebody I know who's getting a knee replacement, and just fabricating bones would be impressive enough. But then organs, tissue. Wow.
Yeah, so we can replace all sorts of different things on our bodies in a very very near future. Plus, I mean, the cancers that used to kill us at 50, they cure them, and you can live to 70 now. You might still die of that cancer again, fine, but they just added 10 or 20 years to your life. And
Yeah.
exercise physiology, nutrition science, gerontology, the study of old age, all these things are massively increasing human lifespans, and we are poised for a dramatic increase in the very near future.
Just like you were saying, I don't remember if it was on the podcast or a conversation we had off mic, but you were saying that we were, and then now this.
Yeah.
Very
But
interesting.
just like escape velocity off of Earth, there might be additional factors that people haven't quite considered yet. Like, it's one thing to get
Hmm.
off the Earth and go to the moon, and you need to be going really fast. But if you want to go to Jupiter, you don't need to escape the Earth's gravity. You need to escape the sun's gravity.
Oh, wow. That's a huge good point.
Even
Huh.
though we are, pretty far away from the sun already, and so you maybe think between the Earth and Jupiter, there's not that much solar gravity you have to take care of. It's actually greater than Earth's gravity. It's actually like 10,000 times Earth's gravity.
Speaking of which, now you've got me thinking because tractor beams,
Yeah.
we were watching some science fiction over the last weekend, and tractor beams come up all the time. If you got your spaceship, shuttle, whatever, out of Earth's gravitational pull, I imagine you're kind of drifting around. The moon's out there in the distance. Earth is too. Nothing in particular is very close. If you were just like floating there for an indefinite amount of time, would the sun eventually attract you enough with its gravitational pull that
Yep.
one day you are just drawn right into the sun?
Yep. Theoretically at infinite
Wow.
distance, but there'll be other things interfering. So if you're less than halfway between the sun and another star, and you're not moving with respect to the sun, you will start accelerating towards the sun. Very slowly at first,
Interesting.
extremely slowly, unnoticeably slow, but eventually you will be sucked into the sun.
Yeah, it's just like sitting in a body of water that has just the slightest amount of current. You wouldn't notice it at first.
Yeah.
Hmm. I never thought about that. That's fascinating.
Yeah. In fact, the Earth would do that too, except we orbit the sun.
Hmm. Speaking of planets, though, Rob,
Yeah.
this got me thinking the other day. While speaking of the science fiction that we were watching, we were catching up on the Disney Plus television show called Mandalorian. Are you familiar with Star Wars? Have you heard
Am I
of
familiar with
George
Star
Lucas?
Wars?
Well, a lot of people are tired of it.
Dude, man, I saw Star Wars in the theaters, man. I don't think you probably weren't even born yet.
No, I wasn't even a twinkle in my parents' eyes yet. So
Yeah, no, I was in third grade, I think.
nice. Oh, that would have been the perfect prime to be, yeah, watching Star Wars.
Yeah.
Brand new stuff. Did you know that in an edited scene of that first film, there was a scene between Han Solo and a guy playing Jabba the Hutt because they hadn't decided to make him into a space slug yet.
Yeah, and they put that into the remastered versions.
Solo! Pinapanoia, Solo!
Right here, Jabba.
It's very sad. It's just so sad.
And in fact, one part that didn't make any sense in that remastered scene at all is all of a sudden Jabba goes like makes this funny coughing sound.
Yeah.
Look, Jabba, even I get bored sometimes. You think I had a choice?
Well, it's because Han walked behind him and they
Yeah,
had to do
he's
something, so they
walking
pretended like
around
he
him.
stepped on his tail. But it's not clear from the scene that he stepped on his tail. He just coughs. I never liked the remastered ones. I thought all the CGI was really hokey.
Me
I mean,
neither.
the dinosaurs on Tatooine, just come on, man, that's just dumb. So anyway,
I'll let it pass. Some of the dinosaur stuff, but that scene there with Jabba the Hutt was just so stilted that I just shake my head when I see it and I laugh.
Yeah.
But one thing I did like about the scene was that even then, when they were making the first film, they had the costume for the character Boba Fett, who has the Mandalorian armor. And he is on the set there in the docking bay where the Millennium Falcon is, watching Han talk to Jabba the Hutt.
Cool.
Who would have thought? And so the reason I bring this up was because Mandalorian is very fun to watch. So we had the whole family together.
I've had people tell me that it's the best sci-fi series ever.
I wouldn't be able to argue against that.
Wow.
I don't know if I would say it's my favorite or that it's the best executed or it's the most brilliant story, but it's got a lot going for it as the overall.
All right.
Yeah. So you got to watch it sometime, but I would understand waiting because when you start, you're going to want to binge it.
Yeah. Well, I want to cancel my Netflix and sign up for Disney Plus, but the girls want to keep on watching some stuff on Netflix, specifically Lost in Space Season 3. Has not out yet. Now, once it's out and we watch it all, maybe I'm going to be switching over to Disney Plus, but we'll see.
That's a good idea. Okay, well, so here's the thing. Then you could probably relate to this as a television viewer, someone in the audience. You're watching The Mandalorian. When you do, you're going to notice how different it is from Lost in Space, maybe in this one way. In Lost in Space, they stay on one planet pretty much all the time, right?
Basically, yeah, the 2 seasons are in 2 different places, yeah.
Okay. Well, in Mandalorian, every episode, the main character is visiting another planet or a space station or maybe a bigger spaceship.
I heard Tatooine mentioned. I'm like, oh, come on, man. What's up with Tatooine? I mean, how much stuff can happen in a one little dingy dust ball around a forgotten corner of the galaxy? Come on, expand your horizons, buddies. But okay, this is good to hear that they're in different places.
Yeah, no, I feel you. I've been just very surprised by how often they're coming back to that planet in the midst of this show when they made it abundantly clear in the movies that no one ever goes there except for the case of the movies. But here we are. Yes, we're still going back to the home planet of the Skywalkers. Doesn't make any sense. But this got me thinking.
Okay.
They are visiting all these new worlds, Rob, in every episode. And this was a great idea for a main topic of Equinox. Because here in the solar system, we have our planets for this solar system.
Yes.
Plenty of them. Not many very inhabitable. And then this got me to thinking, because it's not really explained in Star Wars, but there are a lot of inhabitable planets. And I think that kind of thing has an influence in the back of our mind in just our general trivia about the world and the universe abroad as we know it. And people would probably say, there's a lot of planets of very uninhabitable, very hostile worlds. But the more and more we see all these sci-fi depictions of very inhabitable places in Star Trek and the like, Star Wars, it makes you just tip the scales and begin to think, yeah, there's tons of planets out there and a lot of them that could probably sustain life. And that begs the question, what do we actually know about planets outside of our solar system?
And what a fascinating question that is. the audience, understand that Joe asked me this last week, and I was so excited about this. This is what got me all fired up to do this episode. So we will be discussing this. But what do we know? Man.
Yes, Rob. What do we know? What we're really saying is, what do you know?
Do you remember when the first reports of extrasolar planets started coming out? This is 1992, 1995.
Yeah. Honestly, I remember hearing those things. Yeah. I really found astronomy awesome.
Oh, yeah. But remember the Christian community? I remember a lot of people scoffing. That's not true. They don't know that. And there was a big resistance. And I'm like, this is cool, man. Oh, this is fascinating. I had no problem with it whatsoever. But a lot of people I know were really poo-pooing the idea. Or how do they know that? You can't see a planet around another star. That's just, well, you know the famous Arecibo radio telescope in Puerto Rico?
No. Remind me? Is
You've
this
seen
back in the
pictures of it.
90s?
One of the James Bond movies, there was a fight inside the dish. It's basically a dish inside a volcano, and it's pointing straight up.
Oh, okay. Cool.
And recently they had some damage. A couple of guide wires snapped and part of the dish collapsed. And now they're like, oh, we need money to fix this. And everyone's like, why do you want to fix that old thing? But okay, that's another story. This radio telescope is pointing at a couple of stars, and they were able to measure a change in the frequency of the radio frequency light arriving on Earth.
Okay.
Using something called Doppler Spectroscopy.
Doppler Spectroscopy.
So this is method number one. There'll be two methods we'll talk about today, but method number one for detecting extrasolar planets is Doppler spectroscopy. Now, you know what Doppler is. You know what the Doppler shift is, right? Train goes by, it goes...
Yes.
Okay.
Yes.
That's a Doppler shift. The frequency depends upon what direction the thing is traveling. When it's traveling toward you, the sound waves pile up on each other, and the frequency goes up. When it's going away from you, the sound waves are stretched out and the frequency goes down. And you can tell how fast something is moving based on its Doppler shift. If you know the expected frequency, like if you had a tuning fork and it goes bing, and if you threw that at somebody's head, it'll go bing. They'll know what's coming at their head. They'll hopefully duck. But the frequency depends upon what direction it's going and how fast it's going. And so if you point a radio telescope at a star and you measure its light, it's the frequency of the light coming out of that star, and all of a sudden it goes up or down in a periodic manner, you can say that star is wiggling. Sometimes it's moving towards us, sometimes it's moving away from us. Or even if it's moving toward us or away from us in general, sometimes it's moving a little more slowly or a little more quickly. And they're able to use Doppler spectroscopy to measure a 7 meter per second change down to 7 meters per second. Anything bigger than that is a little easier. So the frequency is, just a fraction, just a tiny fraction greater or a tiny fraction smaller, but it's a little more red or a little more blue. And if that happens periodically, they can say, oh, wait a minute, there's a planet. In fact, if you know the brightness and type of star, you can estimate its mass. You can estimate the mass of the planet.
Oh, okay.
And based on the period, you know how far away from the star it is orbiting.
Huh.
And so you can detect a Jupiter-sized planet using that technique. Anything smaller doesn't move the star enough. Anything bigger, it's easier. But you can get down to a Jupiter-like mass, and it really helps if it's really close. So something the size of Jupiter orbiting at the distance of Mercury is going to make the star wiggle a lot and frequently. Something the size of Jupiter orbiting at the distance of Jupiter would be almost impossible to detect because because the orbit is so slow. You can't, point a radio telescope at the same star for 50 years.
That makes sense, yeah.
All right, but this is cool.
And even if we could, would we?
No, we wouldn't. Well, plus you can't because the Earth is moving. We're rotating. You need a telescope in outer space, not an earthbound telescope, which we'll get to later.
Okay.
So there's a star. In 1995, after Arecibo, they said, oh, there must be some terrestrial mass planets orbiting a pulsar. Now, a pulsar is a tiny little star. It's not big like, our sun or even bigger like other stars. It's a tiny little star. And so if you had a large planet around a little star, you can make it a wiggle and you can detect it. But in 1995, in the direction of Pegasus, a star called 51 Pegasus b, they detected a giant planet in a 4-day orbit around the star.
Oh, only 4 days.
4 days. Now, Mercury is 88 days with a little bit of a relativistic change in there, but it's 88 days. And this planet is as big, a Mercury-sized planet in a 4-day orbit. I mean, it's almost touching the star.
Yeah.
And it's only 51 light years away. It's a very close star. So because it's close and because it's a giant planet orbiting it in a very tight orbit, they were able to use Doppler spectroscopy to detect it. That's really cool. And that is applied science 101. You can't get any better than something like that. And we got, gravity theory, we have light theory, and everything else. I mean, it's just the coolest thing, but there's a tremendous limit. I mean, it's no surprise that the first discoveries were of large planets that are relatively close. No surprise at all. Those are the easy ones. That's a low-hanging fruit. The detection of something like the size of the Earth orbiting at the distance the Earth is orbiting from our sun would be extremely difficult. And there's essentially
too bad.
There's essentially no Doppler shift with the Earth and the sun. Now, Jupiter does move the sun. On Earth, if you're looking at where the sun is, if Jupiter is off to the left, the sun will actually be a little bit behind where it should be. If Jupiter is off to the right, the sun will be a little bit ahead of where it should be. And the sun can move more than the diameter of the sun in the sky, which is 1/2 degree. So if you want to calculate like sunset, you can't just calculate sunset straight up because the sun wiggles. Now, we don't notice it because everything is gravitationally balanced, but the sun is not always in exactly the same point in the sky as far as the stars are concerned at exactly the same time every year because Jupiter moves it. But that's not, there's still no Doppler shift there. It's not like the sun is moving fast in one direction or fast in another direction. So we need another method. You want to take a guess of what the other method might be?
Honestly, it would be a shot in the dark, and that's no pun intended.
Perfect. What would it be? Take a guess.
Well, it has to do with light.
Yes.
It has to do with... See, my mind goes to like long exposure time of things, but why? That doesn't help anything.
Oh, no. You exactly need long exposure time. You are thinking beautifully, perfectly.
Really? That was just too obvious to me.
Yeah.
Should I be an astronomer?
What would a long exposure time give you? If you pointed a camera at a star for long enough and you knew exactly the light output of that star, what happens when a planet around that star comes between you and the star?
Well, yeah, my mind's there. I can see. I mean, frankly, you just wind up getting the planet's dark side facing the telescope, facing your camera lens.
Yeah, you get a dark spot.
So you can see the dark spot. Even if it's a long exposure, it would show up like a streak.
You cannot image a star like that. Stars are points of light. There's only one, maybe two stars that have ever actually been imaged as far as the surface goes. Actually, it's probably more than that now. But forever, we didn't have magnification power in order to see the size of a star. They're just points of light.
Interesting.
But a point at a specific brightness, what happens when a planet passes between us and the star?
Well, it kind of creates just the shadow, the streak of darkness across the star's light.
Yes, but again, we can't see a streak. But what happens is the brightness goes down.
Yeah, okay.
Okay, so what if we took a camera and pointed it into space and just left it there and let it measure thousands of stars for long periods of time? And
That's what the Hubble Space Telescope has been doing, right?
No, because the Hubble is in orbit around the Earth. It doesn't stay still.
Not long enough. Okay.
Yeah. But we did launch a telescope called the Kepler Space Telescope.
Kepler.
Brilliant. 5-foot mirror, 94 megapixel camera.
Oh, that's nice.
And this was launched in 2009. How much did a 94 megapixel camera cost 11 years ago?
As much as all the cameras of the world.
Probably. And it's out of focus on purpose. It's on purpose, not perfectly in focus.
Well, then in that case, it may be a little cheaper.
Well, no, it has to do with the focal length. The camera is not quite in the right spot on purpose. I don't exactly know why, but I think what they wanted to do is they wanted to spread the star out to as many pixels as possible on the camera detector to make the image large.
Okay, I'm with you so far.
And what they did was they put this in a really interesting orbit. It's actually in outer space. It's orbiting the sun, not the Earth.
Oh, okay, that's a good idea. It
And
also would have a much larger orbit then, and
Yes.
it would not move as fast.
And it doesn't move as fast. It doesn't turn nearly as quickly as like it was orbiting the Earth. It's orbiting the sun, is trailing the Earth and a little bit outside the Earth's orbit. So every orbit it gets a little bit further away from the sun. And this thing has been pointing at the same patch of sky. It's now decommissioned, I think, but for a long time, it was pointing at exactly the same patch of sky, a little teeny patch with tens of thousands of stars, but not anything like the entire viewable field of space. And it started detecting dimming and brightening of stars. Now, here's a problem though. Stars are not constant in their light output. Our sun is not constant in its light output. It varies 1 to 2% per year, seasonally, decadally. The sun changes its brightness over time. And if you wanted an Earth-like planet to pass in front of the sun, I mean, think of how large the sun is compared to the Earth.
Oh, yeah. Even Jupiter, yeah, it's insane.
How much of a shadow would this cause? It's like 1/1,000,000th of the output of the star.
Yeah, it would have to be a really good camera, a really good exposure. The conditions would have to be just right.
Yes, and you get just right in outer space. There's no weather. And the exposure is a very long duration exposure, so you can get a really good read on the light output of each star. And you can know its variability. And then if all of a sudden it dims by 0.001%, you say, aha! I think we just saw a planet. But you might be wrong. So you have to wait for the planet to pass in front of the sun again.
Oh, okay, that makes sense.
And then you have a
Lightning
period.
doesn't strike twice in the same spot.
Exactly. And then you have the period of the orbit. And then you wait for a third time, and that's your confirmation.
Okay, that makes sense. But okay, so what you're saying, Rob, is if we don't have a planet flying between us and the star's light,
Then you
we
can't see it.
still can't detect them. Oh,
That's
okay.
right.
Wow.
And so we're only talking about solar systems where the plane of that solar system is pointing at our Earth. If the orbit of the planets is perpendicular to us, it's totally invisible. We will never see it.
That's too bad.
So assuming, random orbits of each solar system, because who would ever expect all the solar systems in the galaxy to be lined up, But if assuming randomness, most of them are undetectable, and a fraction of them, I don't know, maybe an eighth of them, a tenth of them, I don't know, would be detectable using this method. So whatever we count, multiply by X to get the real number. This is totally cool.
That really is. I wasn't expecting it to be such a limited option, but it's also very impressive.
Yeah, except the Kepler Space Telescope broke.
Oh, huh. Okay.
There's the
How
things
long
called.
is it going to take for us to get a repair crew out there?
Oh no! It's toast. It's gone. But I mean, it broke in the middle of its run. It was a giant disappointment. First of all, it didn't quite have the clarity that we wanted and the resolution we wanted. I think maybe because stars are more variable than maybe they expected. I'm not sure. I guess they probably knew it already, but it didn't give us what they wanted, and then it broke. And so it's flying in outer space, unreachable. I mean, you can't send a space shuttle, out there. And what do you do? And the reason it broke, there are these things called reaction wheels. It's a really interesting way to keep a satellite pointed in the same direction. Now, you could use thrusters if you wanted to, but then you have to have little rockets and a lot of rocket fuel on board. There's a lot of weight. What a reaction wheel is just a high-tech gyroscope. You played with gyroscopes?
I have.
Okay. You know what happens when you try to turn a gyroscope? It doesn't turn. It wants to stay in the same direction.
Yes.
So
Yeah,
essentially,
it may wobble a little bit.
and they do because of gravity pulling them down. It's called precession. But without any gravity, if you spin up a gyroscope, it just stays there and it doesn't want to turn. So if you slap some gyroscopes on a satellite, you can keep that satellite almost perfectly positioned and it will not change direction. If you want to make it change direction, you just take the motor powering the gyroscope and spin it a little faster. And because of the conservation of angular momentum, which will also be a really cool episode of Equinox, write that one down.
Okay.
Because of the conservation of angular momentum, if you juice a gyroscope, it's going to induce a torque, and your satellite is going to twist into a new position. So you can extremely precisely balance a satellite with 4 reaction wheels. You need at least 3, but with 4, you can do a great job. But as we're finding out, the company that was making these reaction wheels, which were used in many multi-million-dollar satellites, learned that the reaction wheels did not have the lifetime that they expected.
Oh, okay.
Apparently, the space environment was a lot more harsh than they had predicted, and the lifetime of these things is too low. And now everyone's like, they're mad at them. It's like, you promised us 10 years and you gave us 3. Come on, man. That was an expensive satellite.
Oh, I'd be too.
So it was left with 2 functioning reaction wheels. And you can't balance a satellite with 2 functioning reaction wheels because you can still spin. Like if you draw a line between those 2 things, you can still spin around that axis. You need a third one to stabilize, so you have a 3-point stabilization. One of them would run in one direction only. The other one was totally dead. They're like, oh man, we're toast. We can't keep this thing pointed in one direction. It's worthless. And so they sat down and they said, okay, what can we do? And some people brainstormed this out and they said, oh, no. We do have a third arm, like a tripod. The solar wind.
The solar wind.
The solar wind is always pushing from one direction. So if you have 2 reaction wheels and a pressure from the solar wind, if you can balance because a satellite, it's irregularly shaped. It's not like a bullet. It's got things sticking off here and this over there. But if you can get all those things balanced with respect to the solar wind and 2 reaction wheels, you can keep it. You can't keep it pointed at the same part in the sky, but you can keep it not, how do you say it? If you were facing the sun and you were using a solar wind to balance and you had 2 gyroscopes in each hand, you could always face the sun, even though you're orbiting the sun.
Oh, okay.
So you'll turn around once per year, but you can stay facing the sun. It's a guaranteed direction.
Yeah.
Okay. So now it's now Kepler has finally finished, but they launched a second thing called the K2 mission. That's Kepler 2. And this is similar to before, but instead of pointing at one part of the sky, they're pointing behind the Earth at things that the Earth would see if we look behind us in our orbit. And so they pointed at one space and slowly turned the satellite until it got too close to pointing at the sun. Because if it points at the sun, the camera would be ruined. And then they pointed another part of the sky. And as it orbited the sun, they'd slowly twist it. So it's always pointing at that part of the sky. And then they'd move it to point at a different part of the sky. And so they give it new life. And they were able to image all these stars that they hadn't planned on. And they were able to orbit them, to image them for a long time. But the thing that they're
awesome.
The thing that they're able to detect are large planets around small stars. So brown dwarfs and things like that. But still, that's really cool. It's a whole new field of science that they did not anticipate being able to do, even though the original plan kind of failed halfway.
Yeah.
So good for everyone that, go humans, essentially. We figured out something really cool. And instead of a giant piece of space junk, we were able to use this to do something different. And again, it was detecting light changes around other stars. But again, the percent change is so tiny. You need a lot of math and a lot of really cool, you need a lot of math and a lot of cool engineering to pull something like that off.
So, Rob, then this raises a question.
Yeah.
It must be a couple of times a year I come across a headline that scientists have discovered another Earth-like, potentially inhabitable planet. And then
Yes.
they'll be saying, yeah, we found this planet around a star with a random code name. And who knows? Uh, you're saying that they're not even finding planets that are in the ballpark of Earth-like conditions, or maybe theoretically, other things about the planet would be checking some boxes, like it would have to have uh, you know, maybe some breathable air, or it would have to have a flat I don't know,
All right,
like
hold that thought.
whatever the
Hold that
conditions may
thought.
be, it'd
Seriously,
have
that's
to have a solid surface. Yeah.
let's talk about tests first, and then we'll get to that exact
Okay.
question that you just asked.
All right.
All right, so we
Please.
launched another satellite. It's a replacement for Kepler. It's called TESS, the Transiting Exoplanets Survey Satellite, TESS.
Okay.
And
Yeah.
again, this is a really cool thing, and it's strange. It's orbiting the Earth, but it's in a highly elliptical orbit. It goes out as the apogee. It goes out about the distance of the moon, but it comes in close to the Earth, so it orbits a lot faster than the moon on average. It actually
Oh
orbits the
yeah.
Earth exactly twice per lunar month.
Oh wow.
So it's in a 2-to-1 resonance with the moon.
That's interesting. Huh.
Imagine that you're on a swing and you're kicking your legs, and you're kicking your legs the wrong frequency. You
Oh
don't
yeah.
go anywhere.
One's a little faster than the other.
Or no, just you have to kick your legs at the frequency at which you're going to swing in your
Okay.
pendulum.
Yeah.
And if you do it wrong, you don't move. But if you kick your legs at exactly the right frequency, forward and back, you'll start to move and you go higher and higher and higher, and you're resonating. Well,
Yep.
this is a resonating orbit. It's another way to stabilize an orbit. In other words, every time it does it just right, the moon gives it a little kick. Then the moon gives it a little kick. Then the moon gives it a little kick.
Oh,
In a
nice.
perfect
Interesting.
resonance, and it's a very stable orbit. Remember, many episodes ago, we talked about Lagrange points?
Yes.
Those are places where the gravity between the Earth and the moon, the Earth and the sun are perfectly balanced. So you can park a satellite there, and it'll stay in that exact spot. You might have to adjust a little bit when Jupiter passes or something like that, because there are other gravitational bodies in the solar system.
Yeah.
But you
Yeah.
can park it there, and effectively it's free parking, and the thing won't move with respect to the Earth, and it'll just sit there. It's really cool. Well, this is a spin-off on that idea. And instead of being in one exact place, you're actually orbiting, but the lunar gravity and Earth's gravity are so balanced according to the orbit that you're just bing, bing, bing in an extremely regular and very stable orbit. They think it's going to sit there for about 10 years.
That's impressive.
That's really neat, with very little energy needed. They don't have to adjust the orbit hardly at all. So now they have a stable orbit. They're pointing this thing at all these places in the sky with a better detector, and a better camera, better mirror, better electronics, faster electronics, really good signal feedback to the Earth, and they've taken all these really, really beautiful pictures as they're measuring the light intensity. So, I want you to take a guess. We started detecting extrasolar planets in 1992. The number in the notes is not true. I changed it. It's there so I can remember what the real number is. So not looking at the number that I typed down. It's a code.
Okay.
How many do you think we've discovered? 10? 100?
Well, I would guess it's an unusual random sort of thing because the conditions are not repeatable.
And what order of magnitude? Millions, thousands, hundreds, tens?
No, tens. I'm going with tens.
All right, 4,301.
What? That's incredible.
Now, this is where the applied science comes in. It's not magic. It's following all the rules that we've talked about, all the scientific principles that we've talked about on Equinox all this time now. Is following everything. Everything lines up. There's nothing suspicious about this. There's nothing conspiratorial about this. It's exactly as it should be. Over 4,000. And TESS is going to increase that dramatically.
Wow.
Now, most of the planets, again, are going to be around small stars, but we should be detecting Earth-like planets. And we have detected Earth-like planets. Okay, now we get to your question. What is Earth like? That's a very interesting question.
Right. They would be thinking that it's approximately the same size at
Yes.
approximately a similar distance of orbit to its star,
Yes.
or that the star is similar to our star.
That's even
And
harder. Yes.
so it's like the more things that are in common. So it could be maybe the planet is not really relatively the same size, but it has relatively the same distance to its star, which is
Okay.
relatively the same size as our sun. So there's things like that. I think that they would take some wiggle room and claim
Yeah.
this is potentially inhabitable.
All right. Is Venus Earth-like?
Yeah, I would say that a lot of people would say that it is. No, it's not to me.
No, it
Yeah,
absolutely is. It's almost the same size as Earth. It's almost the same distance from the sun as Earth. It's a lot closer to us than Mars is.
that's interesting. Yeah.
It's very, very Earth-like. It's not in the habitable zone though. Habitable zone. How about Mars? Is Mars Earth-like?
Mm, Parts of Mars look like parts of planet Earth.
Well, it's a rocky
You
planet,
could
right?
say.
Doesn't have much of an
Yeah.
atmosphere, but we can almost live there. I think it's got 1/3 the gravity of Earth, if I remember correctly. And the day is almost the same length, a little longer, maybe hour or two. I don't remember what the Martian one sol was on Mars, 25, 26 hours, something like that.
That's not
So
bad.
it rotates like we rotate. It's a rocky planet.
Yeah.
It's around a very stable sun-like star, obviously, because it is the sun. And yet, why would anyone want to travel across space to find a rock like Mars? Honestly, I would rather stay on my spaceship
You really?
because going down to Mars, in some cases, that's a one-way trip.
Yeah.
I mean, you
Wow.
need a lot of energy to get back off of Mars again. You go there and you land on, why would you do that? Why not, send robots down there and send raw materials up and you can just build a giant space station around your star? That makes more sense to me.
Hmm.
But if that's
Good
true, then you
point.
don't even have to leave our solar system. You want to get off Earth? Fine, go build yourself a space station. Take a asteroid and melt it down into steel. Done.
Ooh, wow. Yeah.
I mean, it's going to be how many billions of years before the sun burns out?
Mm-hmm.
Whatever. Yeah. So if we can't find Earth, really truly Earth-like extrasolar planets, then traveling to stars is a complete waste of time. As far as humans are concerned, I hope we send robots out there and take pictures and send information back. But why would we ever go to those places?
That's a very good point. Even with, mankind going to visit, say, the planet Neptune, we don't really need to see that up close.
Yeah, you can't land on it. You can't touch it. The sun is really cold that far away, so you can need nuclear power, which is fine. But let's send robots to Neptune. Let's send robots to Saturn even. My daughter, she's dying to go to Saturn. She wants to be an astronaut and she wants to go to Saturn. She doesn't realize how far away it is. And we think Mars is far? Man. And Jupiter, that's way out there. Saturn's even further. It's so far away. And there's no reason to go there for humans. Anyway, so we have all these Earth-like, we have all these extrasolar planets. A small fraction of them, they say they're Earth-like. They might be able to start detecting atmospheres around these things based on the dimness curve. They might be able to estimate the mass based on how much of it blocks out the light. They know the orbital period. And so they can start saying that, this is in the so-called Goldilocks zone. Not too hot, not too cold. Most planets are not there. Most of the planets we've detected are not anywhere close. Now, the problem is that every time I see a picture of an extrasolar planet, some artist has drawn this fantastically green swirly thing or this rocky thing, and it makes people think that that's what the planet is actually like. But we have no clue. We don't have pictures of these things. We just know that that star over there wiggles or that star over there gets dim every 83 days. That's all we know. But we've also detected a lot of systems that have more than one planet. That's really cool.
Wow, that is cool.
Most stars, therefore, have planets.
Really?
And they're all different types of planets. They're all different types of solar systems. Now, the ones we've detected mainly are big planets that are close up. That is not a place we could ever, solar system we wouldn't even want to go to. You wouldn't want a Jupiter winging around the sun closer to Mercury. This is going to pull up all these solar flares and gravitational problems and blah, blah, blah. You don't want to go to that solar system. But there's all sorts of weird things and weird combinations, and they didn't expect this. And a lot of this actually causes problems with solar system formation theory. We got enough problems in our own solar system. Maybe that'll be another episode of Equinox, the formation of the planets in, evolution versus creation. That'd be a cool episode. We'll save that one, I guess.
Yeah.
But all these weird combinations of random planets, essentially. And if most stars have planets, and if some stars have rocky planets, they're estimating probably half of stars have a rocky Earth-like planet. That means there's like 300 million Earth-like planets in our galaxy.
Whoa. That's incredible.
Now, that number fluctuates depending on who you're talking to. And so some calculations just last week, I don't remember exactly what the number was, but it depends because there's lots of guesses. If this is true, that's true, this is true, that's true, that's true, that's true, and that's true, then you have X number of Earth-like planets in the galaxy.
Interesting.
But that doesn't mean they're in a habitable zone.
Right.
The Goldilocks zone. It doesn't mean they have an atmosphere. And the worst thing about this, though, is our star is weird.
Our star?
The star at the center of our solar system, the sun, is not a normal star. It's more stable than most other stars. It's most stable than most other stars in general, but it's also more stable than most other similar sized and colored stars. Therefore, given a star of that size with that heat output, most stars throw out giant solar flares. Brown dwarfs, I mean, yeah, if they find all these planets orbiting brown dwarfs, great. They're sterilized with X-rays constantly.
Oh, wow.
You cannot have a habitable planet with a giant X-ray source nearby. And it's pulsating X-rays. It's like having a giant searchlight that's sweeping past, and it'll wipe out any organic molecule on that side of the planet. So most stars are impossible to live around. Even the sun, the so-called sun-like stars, our star is more stable than just about all the other stars. So we're reducing the possibility of finding a place for us to live in the future. There are going to be some, and there might even be hundreds of thousands or maybe even millions. I don't know the number. They'll be out there, and we just got to find them.
Wow. Interesting.
And then the question is, how do we get there? Because physics is precluding us right now. Unless we rewrite the laws of physics, we're not getting out of the solar system. So,
man, this is a lot to chew on because it's sort of like you've brought up with other issues of scale that something is so vast on a microscopic scale between two parts of the atom that it's impossible to fathom the distances and the scale.
Yeah.
We have the same mind-boggling confusion. Speaking of which, not directly related to the planets, but if I understand right, I'd have to take a guess. Okay, Rob, I'm going to ask you a question. You're probably going to volley it back at me.
All right. What is it?
Yeah, so we're talking about the universe, and it's just chock full of galaxies. Galaxies can come in all shapes and sizes, but it seems like none of them are ball-like or cloud-like. They usually take some kind of a shape that is sort of discular. Is that generally speaking true? Are all the galaxies mostly disc-ish shaped?
I would say most of them are probably that classic spiral shape of some form. There are some more globular clusters and globular galaxies, but that system's not stable. Over a very long time frame, that'll collapse upon itself. It has to rotate, or the stars obliterate each other, and it becomes a black hole.
Yeah, that makes total sense, right?
Okay.
So it's got to have some kind of shape to it. Okay, well then if that's the case, the real question is the universe, if you could just like look at all of those galaxies as pinpoints, does the universe have a shape to it that is kind of discular, or is it more circular?
I was sitting in front of Dr. Russell Humphreys at a restaurant, and we're just talking, and because I fidget a lot, there's like I don't know, you know how your coffee cup comes on a little plate, I had a teacup.
Yeah.
And I just put my
saucer.
a saucer. Yeah, I put my finger on the saucer. I started spinning the saucer with my finger. And all of a sudden I said, oh. And I looked at Russ and I said, Russ. He goes, yeah. I said, electrons essentially orbit atoms. Or I said, Russ, electrons kind of orbit atoms, right? He goes, well, not really, but yeah. I said, and the Earth orbits the sun. Yeah. And the sun orbits the galaxy. Yeah. And the local cluster galaxies are orbiting mutually. Yeah. Does the universe rotate? And he stopped and he looked at me. He said, you're not the first person to ask that question. I said, okay. And he said, we can't know.
Really?
Because we only have the light arriving here on Earth today. We can only tell if a star is getting further away from us or closer to us. We can tell if a star is moving with respect to other local stars, but if like all of the galaxies in the universe were moving to the left, we can't know.
Oh, wow. Huh. There's one of the limits of our ability.
On a universal scale. On a local scale, we can detect big movements of galaxies, and it's really weird. It's like rivers of gravity flying through the universe. It's really cool. But if everything was rotating, we wouldn't be able to tell. So I got one last question for you, though.
Yeah.
I want to kind of wrap up with this question, and it's a question of, is there life in outer space, and what does it mean for the Christian?
That's a fair question, especially
Yeah.
when we're talking about planets, because if there is life, that's where they're going to be. It's not like you're going to find a alien life form that can live on a star.
That's right. It's got to be on a planet or asteroid, maybe. But okay. So what do you think? Is there life in outer space?
So I don't think that as a Christian, that the Bible gives us enough of an explanation to suggest that life couldn't exist if it was just a lower creature for God's own good pleasure.
Yes. I agree with 100% there.
But if it was a sentient being with a soul and a spirit of sorts, that's where it gets into tricky theological problems.
Extremely tricky theological problems. Because the Bible clearly says that suffering and death came through Adam. And if you read Romans 8, it's clear that the whole creation is groaning under the weight of that sin.
Yeah.
So it clearly says the whole universe is groaning under something caused by humans. And then Jesus Christ, the kinsman redeemer, came to this earth to save humans, not little green men from Ventriculus Sartori. I just made that up. And so if there is a selfish, bigoted, biased, basically as evil as we are, race of beings somewhere in the universe, they're cursed because of something humans did, and the Savior is human, not little green man, so they have no hope of salvation. That opens up weird theological stuff. But I have no problem of grass, bacteria, even cows on some faraway planet, or maybe a 3-horned cow with 5 eyes and he's got tentacles, whatever.
Right.
I have no problem with those sorts of things. But when you talk about morally accountable life, that is a massive theological difficulty. Now, of course, if evolution is true and evolution happened here on Earth, obviously evolution is possible. And given enough planets with habitable zone given enough stars with a habitable zone planet orbiting,
which we know we now have.
We have at least a couple, yeah. Therefore, if life is possible here, obviously it's possible. And even if it's only remotely possible, given enough planets, eventually it's going to happen. Now, you recall our Origin of Life episode. I don't think there's any mathematical chance at all that life will ever arise spontaneously. Never. So I just totally discount the evolution argument there.
Yeah.
Even the number, given 1 trillion Earth-like planets, life is not going to evolve on any of them. Sorry, boys, it's not going to happen. But the evolutionary angle, they just assume it, therefore there must be life out there. And then we get to the Fermi Paradox. Now, Fermi, of course, a famous scientist involved, I think, in the Manhattan Project. And he raised an interesting paradox. He said, if there's life in outer space, where is it? Because you see, just because life evolves here on Earth 3.5 something billion years ago in their model. What would prevent another alien race evolving 1,000,000 years earlier than us? Some other place in the universe. Maybe even 1 billion years earlier than us, some other place in the universe, or some other place in the galaxy. Could you imagine where we'll be 1,000,000 years from now with our technology?
Why no.
I mean, how many planets will we be inhabiting 1,000,000 years from now if we can keep going?
I again, it's quite difficult to fathom, but
It is.
if we can
It is.
solve the space travel issue,
That's right.
then quite a few, quite a
Okay.
few.
Well, if there is life in outer space, we should be elbows to elbows with alien races. They should be everywhere.
That's the
Because even
thing.
if, like, you know, they they go off to another star, another planet, and they put life on that planet, and 1,000,000 years later they figure out they develop enough infrastructure to spread out to another planet, and it takes all the resources to do that, and then 1,000,000 years later they develop enough resources to go to another planet. Well, given enough millions of years, they will have inhabited the entire galaxy. And based on the
Exactly. They'd be stepping on
probability
top
of
of each
life
other.
forming, that could easily have happened many times in the evolutionary model. Therefore, the paradox is there is no evidence of other life. Therefore, it probably doesn't exist. Therefore, we are alone in the universe as far as sentient life is concerned.
Well, and it also makes you wonder, it's all speculation. Since God, if we go back to a biblical perspective and we're looking for patterns of what God likes to do, he obviously likes to make lots of different types of creatures,
Yep.
as we have here,
Yep.
with a lot of diversity.
Yep. And a lot of different stars and a lot of different types of planets, too.
Yeah, exactly. But that being said, every one that we can account for is uninhabitable besides planet Earth.
Yep. Even Venus and Mars.
Yeah, so even though God likes to have plenty of mankind, he doesn't make plenty of mankind throughout the solar system.
Yeah.
It's something to ponder. When I was in high school, I worked on an idea for a science fiction piece, a novel. For a little while, I wanted to be a novelist.
Okay.
And I had this idea that maybe you could tell a story about 3 planets that each had essentially an Adam and an Eve, a
Yeah.
humankind.
I think this has been done before.
Yeah, but
It's called the Space Trilogy.
I honestly had never heard the premise of the Space Trilogy,
All right.
and I had this
I
thought.
thought that was
Yeah.
some of the most boring of C.S. Lewis's works. Other people disagree with me tremendously, but I didn't think it was a great story. Anyway, go ahead.
Yeah, well, it is an interesting, compelling idea. So, in theory, if God had wanted to, then why couldn't he? Why wouldn't he? So it's not entirely outside of the realm of speculation, but it doesn't seem to stack with plausibility or logic or consistency with theology.
No. Here's the problem. Imagine that there is an untainted, spiritually aware, sinless race somewhere out in the galaxy. What would happen if we contacted them? We, the sinful, evil, murderous, selfish race of humans. What would happen if we contacted them? We would corrupt them.
Yeah.
One of them will get stolen from or raped or killed, or, something would happen. We would corrupt them. We would become Satan to another alien race. That makes no theological sense whatsoever.
Mm-mm.
In fact, my concluding thought for all the notes and all the things I've been thinking of is this. What is the purpose of creation? Why did God create the universe? Well, the obvious answer is to glorify himself, right? What if there's
Right.
another answer? And the answer, I think, is this. I think God created the universe in order to bring about a bride for Christ.
Right.
So we are the focal point of all of the universe. The universe exists so that humans could live on this planet, so a savior could come to this planet, redeem those fallen humans, and so they could live with Christ forever in heaven. That's the reason this whole universe exists. And that changes totally the perspective on what's out there in the universe. There are amazing and beautiful things in the universe that no human will ever see. And God did that for his own pleasure.
Exactly.
And yet,
It's really awesome.
if he had done that, okay, fine. I'm going to build this beautiful star and this ringed planet and this and that and that. But God wanted humans in heaven. That's the purpose of creation. Therefore, what about life in outer space? I don't care.
Right.
If there's bacteria or grass, fine. But we're probably never going to find it. If there's intelligent life in outer space, we'll never find it. Theologically, we won't. And practically, we can't get there. So it's a moot point. It doesn't even matter. It's not there. We are the only sentient beings in not just the galaxy, in the universe. Cool.
On that note, if we were to find grass in outer space or any kind of life form, then the chances are that's only the tip of the iceberg.
Yeah.
A very small tip. We would find a lot more.
Yes.
Finding the first would break open the dam.
Yes. And maybe it's only on 1 out of every 1,000 planets. Okay, give us time, we'll find it. Yeah. I expect that there is life on the moon, though, because asteroids hitting the Earth have ejected a lot of Earth material up to the moon. Now, the life there is dead, but formerly living things are on the moon. I'm talking about bacteria, mold spores, and things like that.
Wow.
I fully suspect that the moon has been contaminated with Earth.
That's fascinating.
Now, the probability of getting to Mars is incredibly remote, and especially in the sterilizing environment of outer space. And then, of course, the heat of reentry and the heat of impact. But there's a possibility that bacteria, spores, or some sort from Earth have gotten to Mars. They might not have lived, but if we find life on Mars, I would put money on it. 1,000,000 to 1. I don't have $1 million, but 1,000,000 to 1. That life came from Earth. That is so much more probable than life evolving by itself spontaneously.
Wow, fascinating.
Yeah.
Good job, man. Thanks so much, everyone, for joining us on this quest. If you found this episode interesting in any way, consider sharing it with your friends and families. And if you want to dig deeper into any of this topic, you can find all the links to stuff that Rob introduced in the show notes on our website. We're available at nightowl.fm/equinox/36. The show notes are also with this episode if you subscribe to the show in an app on your phone. And you should also check out Biblical Genetics, Rob's other project, and he put out another video very recently. Looked pretty good. Biblical Genetics is also available on Facebook and YouTube, so if you want to, you can jump into the comments section and join in discussions anywhere that you prefer to get that kind of content. If you want to find me, I'm at JCS Darnell on Twitter, or take a listen to my other podcast now, Hi-Fi, that is a tech podcast. We just reached episode 10. It's available at nightowl.fm/hi-fi. And until next time, goodbye, Rob.
Goodbye, Joe.
You have been listening to Equinox. So one other thing that has crossed my mind is at the core of planets and moons, do they vary a whole lot? Take out the gas giants.
Yeah.
For those that have rock and metal and things like that, are they generally hot or cold? Or is it all over the place?
It's all over the place. Most of the ones we've detected are hot because they're close to the star.
Oh, okay.
Because they're easier to
So is
detect.
the idea that the closer to the star, the hotter the core will be?
Oh, the core of the planet. I'm just thinking about the surface.
Yeah, I was asking about the core.
We can't tell. We don't know if that thing is still a molten blob or if it's cooled or if God created it cold or hot. We have no clue. We can only detect the size relative and maybe its mass.
Oh, okay.
That's it.
Would you say it's most likely cold?
I would guess that planets out there are most likely like similar in many ways to the planets around our sun.
Okay, that
I
that
would be
does make sense.
surprised to find a planet that's still bubbling with molten lava, and specifically because I don't believe in the evolutionary planet forming theories.
Oh, okay.
I don't think they work, and I don't think they can explain where planets come from. That doesn't preclude God making a molten, bubbling planet because he loves diversity and variety. Fine, okay. But as far as the evolutionary story goes, I can't imagine planets forming from protoplanetary disks because the physics tells us that the little particles are going to smash into each other and obliterate each other. Until you have something at least a kilometer in diameter, it's not large enough to not be obliterated when it runs into something else. So the particles continually smash into each other, and half of them fall into the sun. And as they grind away to smaller and smaller particles, the solar wind will blow them out of the solar system. And
Okay.
that's not my problem. That's the evolutionary problem.
Right.
They don't have a mathematical way to explain planets.
Oh, okay.
All right.
Not our problem.
Two-track audio. Here we go. Bum, 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 bow, bum, bum, bum.